Hello everyone, hope you are doing well. Welcome to the online platform Civil Technobricks. Guys, here we will tune for the instantaneous decoding of conceptual knowledge in the field of civil engineering, where study elaborates decoding the earth to build a better world. Guys, today we will see the core concepts related to the engineering applications of remote sensing in the civil infrastructure. Here, the remote sensing that provides the valuable spatial information about the various parameters like land, water, terrain, infrastructure, and environment conditions without direct physical contact. Here, that geospatial advantage of that applications in the remote sensing, which based on the geomatics, where that geomatics depends on the 4M. M stands for measurement, M stands for mapping, M stands for monitoring, and the last modeling. Here, with reference to civil engineering point of view, this cycle which supports the planning, design, construction, monitoring, and management of infrastructural projects. Here, with reference to that remote sensing point of view, the satellite, aerial photography or aerial imagery, drone based data that will more helpful to the engineers to observe and absorb or grab or catch or extract the drone data that will be more helpful to engineers to observe the large areas quickly and cost effectively. With reference to that point of view, the remote sensing will become more powerful when which will integrated with GIS for analysis, mapping, and decision making procedure, so that the shift in engineering field where we are moving from reactive fixes to the proactive planning with reference to the spatial data abstraction. So the map that functions as a filter for information, where we collect, we modify the collected data or the filtered data for the engineer perspective view or the observation or the decision making point of view. So here the data inputs with reference to optical fiber or optical lenses or imagery with reference to the high technology, that is the lidar, radar, or microwave waves we use for that geomatics point of view. Second one, that is the categorization, where we are using that remote sensing for the infrastructural planning, which will be initiated with reference to the land use and land cover point of view. Here we consider or compare the land cover and land use, where the land use is nothing but a function of that land. For that it will be used, and the land cover which will be the material which will be constructed or the product which will be constructed on the earth surface. With reference to that, infrastructure planning requires accurate information about land use, terrain, drainage, then displacements or deformation and natural resources with reference to the land surface. Here, the remote sensing plays an important role with reference to identify the suitable areas for the infrastructural projects like road projects, bridges, dams, buildings, airports, industrial zones, and many more construction activities. So, with reference to that satellite imagery that supports the comparison of different project alternatives before the final site selection. Here, the asphalt shingle where oak and vegetation. So, oak and vegetation which will be the tree, and that asphalt shingle which will be the actual bungalow constructed with reference to the bungalow scheme. Here, that is the actual land cover, where the functioning point of view we see that the single family residence that are with reference to the yellow color. So the whole bungalow system is for the single family residence which will be provided. So that reduce the field survey time and which improves the accuracy for preliminary engineering planning. So with reference to land use and land cover point of view, we see that the levels from level 1 2 3, then level 1 2 3 likewise, where description is urban area or the built up area, residential or commercial point of view, high density residential point of view, agricultural, likewise each and everything which will be classified, where the level is studied with reference to the coding system 1 1.1 1.2, likewise 2, likewise 3. So level 1 third code which will be for the forest. In that forest, evergreen, dense, and open, these three criteria are there. Then agricultural land, which is the level having code 2, where cropland, kharif, rabbi, kharif plus rabbi, plantation, agro horticulture, these are all the parameters. And in the level 1, which will be the built up area, or the urban area, then residential, commercial, high density residential, likewise it will be divided. So that categorization of the surface based on that land use or land cover, which will be more beneficial for the urban planning and monitoring point of view also. Now with reference to the managing the metropolitan cities or the sprawl or the population density with reference to the city area, the rapid land use assessment which will be more useful nowadays. Why? Because the day by day the population is goes on increasing, so that the land use and land cover which is also increasing. Likewise here the gray color which is 1990s urban extent, at the same time at the same city in 2020 after 30 years that urban extent will be exceeded up to that mark. So this is the unauthorized sprawl. Here we see that the remote sensing which is more useful for the planning point of view. So that planning is for the population density, then highway alignment, railway planning, traffic corridor analysis, or any network analysis. So here the satellite images which help to identify the existing city population or the infrastructural land use land cover and the forecasted land use land cover also with reference to the roads, terrain, water bodies, settlements, environmentally sensitive areas also. Here the digital elevation model plays important role to understand the slope analysis, selection of economical transportation routes, and many more assessment tools also. So here the problem, that is census data for the 10-year cycle is too slow for modern growth rates, because in city the industrialization and urbanization growth is too much high. So for that 10-year cycle is too much slow as a census data to analysis. So solution is that we have to plan rapid land use assessment, that is RLA, with the combining of satellite imagery plus local field knowledge, or the solution which is the exact option which is in front of the engineers. So case study which is the Honduras, where 18 land use categories map over 900 square kilometer in just 3 weeks. So time duration is just 3 weeks, but area is smaller area with the 18 land use categories are utilized, so that rapid land use assessment which will be more fruitful for the metropolitan sprawl management point of view. Here we see the corridor optimization and terrain analysis. This is the actual digital surface model, or we can say that the digital terrain model also. With reference to that we check the hilly regions, with reference to that we mark the ridge lines, and in from that valley line, or with reference to the valley line and ridge line, we plan to mark the alignment of the roadway or highway. With reference to that we check the cut portion and fill portion, so that cutting is required and filling is required, which will be marked with reference to that alignment. Also we take the avoidance of that area, because there will be a unstable soil in that position. We have to avoid our roadway, so we have to shift our road alignment likewise this area, or from this area likewise. So here with reference to that, remote sensing is more useful for the highway alignment and railway route planning, where the digital elevation model supports slope analysis, selection and economical transportation routes, where that improves the route feasibility, reduce construction cost, and safety increases with the sustainable approach. So engineering impact of that highway alignment, which is based on volume calculation, soil stability and right of way. Here the right of way which is the overlay cadastral map to estimate acquisition cost. Soil stability which is most important, so that we have to identify the waterlogging areas, that are the dark tones in the infrared bands, which is detected with reference to the remote sensing tool. And first one will be the volume calculation, where we have to calculate earthworks that require cost before breaking the actual ground surface. Most important point, that will be the site selection criteria, which is based on the hydraulic structure suitability and safety, just like the dam like structures. With reference to that, this is the satellite imagery. With reference to that, we check the ridge lines of the hilly regions. With reference that, we get the valley line, and we check this is the actual dam wall, dam structure or corner reflector, and this is the actual reservoir in the valley portion of that all hilly region. So overall water or overall rainfall with reference to that watershed which will be collected with reference to runoff in that valley, so that the whole reservoir will get full 100% after that heavy rainfall. Means that remote sensing that supports the mapping of reservoirs, their characteristics or their nature of flowing, their depth, their width, then reservoir their dimensions, lakes, drainage networks, and watershed boundaries also. Here, we use the satellite data which helps to analyze the surface, or we can say that the water availability within that catchment area. Then we have to cross check the catchment behavior also, land cover conditions, and land use mapping also. Here, that type of site selection on the basis of hydraulic structure, we have to check the suitability and safety, where which is more useful for floodplain mapping, irrigation planning, and groundwater recharge studies also. Here, the geological safety, submergence modeling, and monitoring, these are the three basic and most important parameters. On that, we have to check the site selection, where geological safety based on the faults and fractures, these are the geological components we have to cross check or identify so that we can prevent the leakage in the future. Then next, submergence modeling, where we have to check the simulating water levels to identify the submerged villages. And next one, monitoring, where we have to use the active remote sensing for level deformation tracking, so that we can check the deformation or displacement within that whole catchment area or watershed area also, or the water which will be stored in the upstream side, and that will be impacting the water pressure beneath to that earth surface, we can cross check and monitor. Most important, that is the watershed management, where we use the integrated basin analysis with reference to the layer by layer imagery. So total basic layer will be the topography layer which gives the slope, then next layer will be the soil type, and next layer will be the land cover. So here we check the satellite blue or morphometry, that gives the analysis of the drainage density or the watershed density to understand the runoff behavior of that terrain with reference to gradient and slope. These are the characteristics of topography. So here the slope, soil, and vegetation, these are the three conditions: slope, soil, and vegetation. So with reference to that, we check the sediment yield prediction, means what much amount of rainfall will occur in that watershed. So what much amount of sediment will travel from that location to that location, we can check, or from that location to that location also. With reference to that, this is the actual birth, and these are the actual nature of the river. So here we can mark the site selection for any type of dam. So this all fun shape catchment for that watershed, that will be collect the water from various tributaries and main rivers. So here the remote sensing which provide rapid information during floods, cyclones, landslides, earthquakes, and other disasters also. Here we use in watershed management the microwave and radar sensors, which will be more useful because they can collect data during cloudy situation also and rainy conditions also. So our goal is we have to achieve the sustainable mandal level micro planning to arrest desertification, or we have to improve the forestation. Here the satellite imagery more helpful for the affected areas or the damaged areas, damaged infrastructure after disaster, then block roads or vulnerable settlements also, with reference to that watershed management. Then most important point, that will be the flood monitoring. Here we see the pre-disaster zoning and post-disaster assessment. Now this is the actual normal flow of the river, and this is the actual peak flood flow of the river, which will be calculated or captured by the radar. Means we have to analyze the normal flow with reference to the peak flood, that is the pre-disaster zoning and post-disaster assessment. So these overall combined damage assessment, which is based on technology, zoning, and comparison. Why we are focusing this? Because we are using high technology, that is radar, that sees through the rain or clouds, where rain and clouds does not means obstacle for that, where optical sensors fail, so that radar will be more effective to identify the actual damage on the earth surface with reference to the heavy flood. Then we have to mark the zoning on the basis of delineating floodplains to prevent construction in high risk zones. Why we are comparing this pre and post? Because we have to quantify the submerged agricultural land, so that the ruling authority or the government take decision for the remuneration for that. Here the remote sensing provides rapid information during floods, cyclones, and earthquakes also, where the radar sensors are especially useful for collecting the data during cloudy and rainy seasons also. So that supports emergency response, rescue planning, decisions, damage assessment, and further disaster mitigation techniques and its assessment. Next most important point, that is the groundwater exploration, where we have to check the suitability on the basis of hydrogeomorphology, where we have to see the invisible things also. Why we have to see the invisible thing? Because the groundwater which is available beneath to the earth surface, so that availability of groundwater which will be collected after traveling n number of soil layers and n number of rock layers within the earth surface. So here the vegetation anomaly or alignment or the cracks are to be identified. With reference to that cracks and the slope available on the earth surface or the contours available on the earth surface, the rainfall water which will traveling with reference to the valley line through that cracks within to the aquifers or the fracture zones. So here the most important concept for groundwater exploration is dependent on the groundwater is a inferred from surface clues. So we have to identify that groundwater on the basis of indicators just like the lineaments, vegetation anomalies, and paleo channels. Here the lineaments, that are the fracture zones where water accumulates. Vegetation anomalies, these are the healthy trees in tree or dry terrain. So healthy trees in the dry terrain is also the vegetation anomalies that will be identified for the groundwater exploration. And the third one will be the paleo channels, where ancient buried river beds are to be identified so that we can check the exploration or the availability of groundwater. Now the, we have, if we have to check the groundwater without any using the drilling techniques, then we have to integrate our investigation based on some satellite data and resistivity surveys, where we use high drilling success without coring any drill on the earth surface. So non-destructive testing which will be followed on the basis of satellite data and resistivity analysis with reference to remote sensing. Then geological mapping, most important thing, that is based on the lithology and the structural analysis, or we can say the topographical characteristics or ground survey and structural analysis. So two basic graphs are there: spectral signatures of rocks with the reference of wavelength and reflectance, percentage of reflectance, like granite rock, sandstone, limestone. And the second one will be the synoptic regional view, which is based on the color coding system with reference to the contours. So with that, the n number of colors, with reference to that color coding, we have to identify the type of rock which is available in that region. So here the remote sensing that helps to identify geological structures such as faults, lineaments, folds, fractures, rock formations, and many more geological components. These features are most important for foundation design, tunnel construction, dam site investigation, and slope stability, and many more studies. Now with reference to satellite imagery, which supports preliminary geological mapping before detailed field investigation which will be followed. So here the civil engineering point of view, civil engineers study the lithological discrimination, structural mapping, and resource allocation so that they reduces the risk by improving understanding of ground conditions at the project site which is on the earth surface with reference to the geodetic curvature. Most important thing, which is the environmental impact assessment, which is based on the ecological footprints, where we have to mark the noise buffer, that is the impact zone, and habitat fragmentation, likewise the availability of zoning. So environmental impact assessment based on the condition of environment, based on the condition of topography, and based on the condition of disasters also. So here the objective of evidence, which is based on the timestamp satellite data for regulatory compliance. So the remote sensing that allows regular monitoring of the construction progress over large project areas so that we can compare the construction activity at the same time the environmental impact assessment based on that baseline data. So here we have to establish pre-project status of air, water, and vegetation, that are the environmental components, where impact modeling by predicting wildlife corridor disruption. So here we have to check the environmental impact assessment so that the satellite data that supports before and after comparison of project areas to detect environmental changes along with the infrastructural projects they are impacting on the land, vegetative material, water, and settlements. So civil engineer use this information to design sustainable projects and reduce negative environmental impacts, to reduce soil erosion, deforestation, water pollution, and urban heat islands effect. Then most important thing, that is the disaster management, which will be the rapid response or mitigation cycle point of view we study. Here the disaster point of view, we see the specific applications based on warning, recovery and response. Here the rapid response is required. Before that, we have to warn the people who are within that premises or zone, so that the recovery will be more feasible. So warning, that is the monitoring cyclone paths or slope instability. That warning must be 24 hours or 12 hours before of that any type of disaster. Then recovery, which is the assessment of structural damage of that area, and the response, that will be the relief when maps are outdated. So maps are not working. The most important, that is response is required, so that the persons who are affected with reference to that disaster, they can help from the response teams. Here the remote sensing, which allows that regular monitoring or the warning or the response with reference to the remote sensing and GIS based on some contours or based on some ground control points or satellite imagery. So that seismic activities or tsunamis or earthquakes, this type of specific applications are within the disaster. So we have to assess that disasters with based on some changes on the earth surface, like change in the coastal line, change in the river behavior, or change in the water reservoirs of the huge dams. Likewise, next disaster, that will be the landslides. Here we have to identify slopes, instability in hilly regions, or with reference to logistics, we have to navigate washed out infrastructure, so that we can provide the healthy habitat or the infrastructural livelihood to the persons who are living in that area. Most important in application of remote sensing, that is the smart city planning, the information city or the digital twins. Here we check the remote sensing for underground utility integration based on some models, where the sewage water which will be collected and collect out from the away from to the city, so that the sewage treatment plant are to be constructed and they use that water. Also that we have to provide the water for drinking and usage purpose, so that we have to provide the grid. Also we have to check the airflow or solar potential simulation based on some temperature change or the availability of winds. Means the information of city with reference to the digital twins, we have to study from static maps to digital twins. Here the LIDAR technology, which is most important to play the role with on the basis of digital elevation models, or we can say the 3D models. Here creating precise 3D models for flood modeling and solar analysis, which will more helpful to analyze the planning of any type of smart city. Also we can use the modeling for analysis on the urban densification and water demand based on the population point of view. So huge dense population area which require large water demand, likewise we can use. Here the case study point of view, we see the Hyderabad city, that is the urban development point of view. We check the project data, that is the location of Hyderabad and Warangal agency who is working in that premises, that is the Municipal Corporation of Hyderabad and JNTU, Jawaharlal Nehru Technical University. The data source which is required or assess, that is the Indian remote sensing satellite data based on the PAN plus LISAS 3. So key statistics, that is 57.48% decadal growth rate which will be monitored with reference to the zones like green color, orange color, blue color. Here the result is Hyderabad Environmental Information System HEX, which will use system to check the urban development and its impact on the earth surface or the vegetative material or the water bodies. So map 16 specific land use categories. They guided the road widening and zoning, or they offer the guidance about road widening and zoning, so that they also identified encroachment on water bodies also. So this is the actual case study where the remote sensing which will be used effectively to complete the smart city planning or urban sprawl analysis. Also the environmental impact assessment too. The most important, that is the summary and the future scope point of view. Here the future of geomatics in engineering, which is based on the three components, that is the real-time monitoring, unmanned aerial vehicle or drones, and hyperspectral imaging. So remote sensing is an important tool for civil engineering for the planning purpose, monitoring purpose and management purpose also. Here that supports transportation, urban planning, water resource management, disaster management, and geotechnical studies also, along with environmental assessment. So that real-time monitoring and hyperspectral imaging most important for material identification, where hyperspectral imaging is used. Then low altitude and on-demand surveys, drones or unmanned aerial vehicles are used, where real-time monitoring point of view we use the revisit times of satellites which collect the real-time data on the earth's surface. So that integration with GIS of all these 3 points, which converts the satellite data into practical engineering information. And for civil engineers, they use that remote sensing technique to improve the accuracy, mitigate the risk, save the time, reduce cost, and achieve the sustainability approach. Stay tuned, guys. Happy learning.